Okay, my talk tonight is going to be on stellar evolution. So the title of the talk is The Life and Death of Stars, the Life Cycle of Stars in Our Galaxy, and using this to understand our place in the universe. So my name is Karen Pollard. I'm at the University of Canterbury and I'm a lecturer there. Just a little bit about myself. I just want to talk about some of my background. I did my PhD at the University of Canterbury in astronomy, and my first job was in Cape Town in South Africa at the South African Astronomical Observatory. And that was a really interesting time to be in South Africa. In 1995, Nelson Mandela had just come to power, and so there was a lot of changes going on in the country at the time, and it was a fascinating era to be there. And it was also a very good place to do astronomy. The South African Astronomical Observatory was a research observatory, lots of very active people there, so it was a really good place to be a postdoc. Then I came back to the University of Canterbury from 97 to 2000 and was working on variable and pulsating stars. In 2000, I went to America. I went to Pennsylvania and I was an assistant professor, a teaching position mostly, although there's a little bit of research there at Gettysburg College. And they had a really good local campus observatory, and that was very interesting. They had a very similar camera to what we've been using at Mount John. In 2001, I came back to Canterbury as a lecturer, and I've been the director of the Mount John Observatory since 2008. And recently, I was a visiting ESO fellow in Chile at Santiago, and I found that very interesting. That was very interesting to go to see the observatories, particularly the ones high up in the desert. And to see the VLT, the Very Large Telescope, all four of them, and to see that facility was really interesting. And they also had, they were building at the time nearby a telescope called the ELT, which is the Extremely Large Telescope, a 30-metre telescope, and that's currently under construction. It was a very interesting observatory to visit and see the research that was going on there. So my particular research interests, I'm interested in stars, stellar variability, stars that are pulsating or stars that are in binary systems that may be orbiting each other. I'm interested also in the composition of the stars, what chemical elements make up the stars, and particularly interested in the stellar evolution. So essentially what stage of evolution they are. Some stars pulsate when they're near the end of their life, but other stars pulsate at different stages of the evolution. So the top picture here in the diagram is a star that's quite old and it's shedding mass into space. The diagram below it, the picture is pulsations in a typical star like the Sun. We can look at the various type of pulsation modes that young stars undergo. You can also look at young stars, and this picture, the third one down, is a picture or an artist's impression of Beta Pictoris, which is a bright young star in the southern hemisphere. It's visible to the naked eye, and it's very interesting because it's young. It's about 20 million years old. And it's interesting because it has a newly forming planetary system around it. It's known to have at least one massive planet, probably two, and we can also see the signatures in the photometry, that's the light output, and the spectroscopy of comets falling into this young star. And we see the absorption that's happening as these comets fall in and evaporate. So that's what we call protoplanetary disk. Or a debris disk around this young star. I'm also interested in young massive stars. This one at the bottom here is an image of Eta Carina, So this is a star, a massive binary star. So two massive components orbiting each other, and they've had various outbursts in the past. And this is a Hubble Space Telescope image of it, where you can see some of the material that's been outburst from the star. So this is a young massive star. It's not going to hang around very long because it's already unstable and will go bang at some stage relatively soon, although in astronomical terms that could be not for millions of years. Okay, so today I wanted to talk about stellar evolution, essentially not evolution in the biological sense, but evolution in the terms of the life cycles of particular stars. So first of all, I want to talk about how stars and planets form, and particularly want to look at normal stars. What are they like? How do they shine? And talk about the processes by which they give out light and energy. And why do stars evolve is one of the critical questions. And then I'll move on to talk about two examples of life cycles of stars. So usually I give an example of a low mass star and a sun. The sun is a very good example of a low mass star, and it has a fairly typical evolution. And then we'll talk about a more exciting star, a high mass star, something that maybe is 25 times the mass of the sun. And these stars evolve very quickly and very dramatically, and so the high mass stars can be quite exciting, and they provide an interesting contrast to the low mass star evolution. And then finally, I just want to finish up by saying we'll tie all up the stellar evolution with looking at our place in the universe and seeing how we came to be here on the Earth, in the solar system, in the galaxy. And we have a look at the journey that we travelled along to get here in terms of where did the chemical elements come from, how did they form things like the solar system, the planets, and eventually life, so that we can exist here on the planet Earth. So I want to start off by talking about how stars and planets form. We'll start off by going to the Mount John Observatory, and we have a look up at the sky. And so when we look up and see the stars and the Milky Way, we have to remember that we're seeing our galaxy from the inside. So when we look up and we see this Milky Way galaxy, and we see the millions and millions of stars that make up this part of the Milky Way, and then we see the big dust lanes, we actually can't see the real structure of the galaxy, because we're seeing it from the inside, as I said. And so our location, when we look where we are in the spiral arm, so we're the sun here at the position indicated, and if we're looking towards the constellation of Sagittarius, we're looking towards the centre of our galaxy, and so we see the Milky Way galaxy will bulge out at that point. So when we're looking up at the sky, we see that bulge of stars in the Milky Way. And because we're looking through the disk of our spiral galaxy from this position, we can see the spiral arms of the galaxy, and we can also see the dust that's entangled in those spiral arms, and that gives you the dark, dusty lanes that we see. So when we look up at the sky, we see this Milky Way, these many millions of stars, but we see these dark lanes that are the gas and bits of fine dust that are the birthplaces of new stars and planets. So new stars and consequently planetary systems forming around those stars form in these spiral arms, and so these are the birthplaces. There's also this interesting feature here. This is you may have a look at this close up. This is known as the kiwi in the Milky Way galaxy, and you can see that sitting here. And so it's the birthplaces of kiwis as well as stars and and planets. Okay, here's a star cluster that people may be quite familiar with. This is Matariki, and you can see Matariki has got this really interesting wispy appearance. There's about 7 or more stars that are visible, depending how good your eyesight is, to the naked eye. But they also show this wispy appearance, this and this blue light, because the stars are quite young. The light is being reflected off the nearby dust, and so you can see this wispy appearance and this blue scattering that's occurring. When you look at this wide field image, you can see that this is an area of the sky that there's lots and lots of dust clouds, lots of gas and bits of dust entrained in the gas. So when we're talking about stellar evolution, this is really important. It's the big, cool interstellar molecular clouds that form the stars. And so these collapse gravitationally to form clusters of new stars. And we can see here this young cluster, Matariki, that's formed relatively recently. So this is a cluster that's a few 100 million years old. So how do stars and planets form? The stars usually form in clusters. So we have this cooler molecular cloud, and there are some parts of it that are denser cores, and so they have more gravity, they pull in more material, and then we get clusters of baby stars or protostars forming in this molecular cloud. Once those protostars get to a high enough density and a high enough temperature, then they can ignite in the inside and nuclear fusion can start. And so we call those protostars or baby stars. And once they turn on, we call them stars, once the fusion processes start inside. So those young stars are quite hot and blue. The big blue dots here are the young stars. They're putting out radiation. And so this yellow area around these stars is where the gas has been ionized. There's enough radiation to ionize the gas, and the gas glows. And so we call that an H2 region or an ionized hydrogen region. And so you see these young stars surrounded by this hot gas cloud, and that's quite an obvious feature. Then we have a young cluster, maybe something like Matariki, when you look at the young cluster. And then we want to study the stellar evolution. So astronomers are very interested in studying clusters and clusters of different ages, because astronomers want to understand why stars age at different rates. And essentially what we're going to see is that the important thing here is the initial mass that the star is born with. So the initial mass is really important, and that governs what's going to happen to it in the future. So stars in a cluster are born with a variety of masses. Often you get a few big ones, and then you get less and less, so a few big ones, and then you get more and more stars as you go to the smaller mass ones. So you have a few big blue ones, quite a few ones like the sun, and then lots and lots of these little red ones when you're forming a cluster of stars. But the big bright ones are the ones that are more obvious, because they've got they're shining brighter, and they're just more obvious. And so they're much easier to see. So stars change with time because they ran out of fuel. It takes a long time, depending on the mass of the star, but eventually they'll run out of fuel, and that will mean the star will end its life. So for a high mass star, or a star like the sun, or a very low mass star, they have a different structure on the inside depending on their mass. But these stars all have the same, start off having the same sort of energy processes occurring in their cores. So as I said, the most important thing about a stellar cluster as it evolves, the most important thing is the initial mass that the star's born with, and that governs what's going to happen to them in the future. So once again, here's a nice closer up picture of Matariki, and this is a young cluster. There's more than 1,000 stars in this cluster, but about the brightest 7 or so, depending on your eyesight, are visible to the naked eye. And they have, as I said, they have this nice wispy appearance so that you can see the starlight of the young bright stars is shining off and being scattered by the gas and dust that is surrounding this young cluster, that this young cluster is passing through at the current time. In recent years, astronomers have found out a lot of interesting things about the way that stars form. And this is, a lot of advances have come because of new technologies. So in this picture, we can see on the left that this is a visible picture of the trapezium cluster in the Orion Nebula, which is a nearby star-forming region about 1,500 light years away. And in the left, you can kind of see 4 stars here, but there's lots of gas, dust, some of it's glowing, and you can't really see much of what's happening here in the visible part of the spectrum. And visible light is often blocked by gas and dust, and so you can't actually see very far into these star-forming regions. So new technologies such as infrared astronomy, and this one on this picture on the right is a infrared image of the same region, and you can see here that this trapezium is just the brightest stars. There's actually, tens, if not hundreds, of these smaller, dimmer, but still the same age stars, but they're just lower mass stars that aren't as luminous. But you can see a lot more detail in this right-hand image in the infrared. So the infrared has a longer wavelength, and so it doesn't see, it's not affected by the dust as much. So astronomers using infrared astronomy have been able to peer through the dust and see what's happening with star formation, essentially been able to look at how many different types of big stars and little stars you get in star formation regions and some of the processes that are going on. And that's been really important as the development of these new technologies. When you have new technologies and new observing windows, you get to see new and exciting physics that's occurring inside places that you couldn't see before, or energies you couldn't see before. So also in Orion, this is the Hubble Space Telescope image, and a close-up of this, we can see that there are young stars forming, and they have young stars, and the leftovers of the material that form the stars flattens out into a disk called a protoplanetary disk around the young star. And these young stars and these young protoplanetary disks are where new solar systems are forming. And once again, this is an optical image. You can see it's quite difficult to see, but in the infrared, this would be much clearer, and you'd be able to see the planetary systems forming there, and be able to study the process of star formation by taking these close-up views and images in the infrared of these star formation regions. So once again, this is an image of Beta Pic, one of my favourite stars that I've been studying for a few years. This is an artist's impression. You can see that it's a young star system. The star at the centre is actually a pulsating star called a Delta Scuti star, and it has one big giant planet, about 8 times the mass of Jupiter, and there's also evidence now that it has a smaller planet orbiting in the interior. And although this is an artist's impression, we can also see the comets that are falling in here, and we do see the signatures of these comets falling into the star and evaporating, and we see those signatures both in the light and in the absorption spectrum that we see from the star. And so this is a very interesting planetary system and young star to observe. Because it's pulsating, we can get some information about the star itself, and we can also get lots of information about the physical conditions in this disk, about the comets, and also about the stars that are forming. the planets that are forming in this protoplanetary disk. So here's a comet. As it gets close to the star, it evaporates, and we see that absorption occurring in the light output. So essentially you can see a transit not by a planet, but by a comet. And this is observations from a space telescope called TESS. So some of the properties of stars, normal stars, what are they like? So the sun is a fairly average star, and when I talk about stellar evolution, I'm going to use the sun as a good example of a low mass star. So the sun and stars are balls of glowing, hot glowing gas, mostly plasma, so ionized gas, about 75% hydrogen, 24% helium, and 1% other stuff. Now, astronomers call this 1% other stuff. We call that metals. Chemists probably don't understand that, but we talk about hydrogen and helium and everything else. And so we often talk about the metallicity of a star is how much other stuff we have besides hydrogen and helium. And so when we look at this as a pie chart, it may look something like that. Okay, another thing that we can tell just by looking at a star is we can tell its surface temperature by the colour of the star. So the colour is closely related to the surface temperature, which is also closely related to the mass and therefore the size for normal type stars. So when we're talking about young stars that have just been born, stars on the main sequence that have just formed out of the cloud of gas and dust, then there's quite a range of temperatures that these stars can have. So the biggest stars may have about 50 times the mass of the sun. They may be about 10 times the radius of the sun. They're probably around 40,000 Kelvin, and they are very hot and luminous, and they have a bluish tinge to them. Now the colours here are exaggerated, but they essentially have a bluish tinge when you look at them. As we go down in mass, we get the temperature gets less and less. The mass gets less and less. So something like the sun is here. It's about 5,800 Kelvin. It's one solar mass, one solar radius. And then these little red stars, the little ones that are quite dim, they have a temperature of 2,500 degrees, and they are quite cool and red. They would have a mass of about 0.1 of a solar mass and a radius about 0.1 of a solar radius. So as I said, the interesting thing is that you can actually see this colour effect when you look at stars in the sky. So here we're looking at Orion on his head as he is in the southern hemisphere. And if we look at Puaka, which is the blue supergiant up here, when you look at it in the sky, you do see it as it distinctly has a whitish blue tinge to it. And then if you look diagonally opposite and you look down at Betelgeuse or Betelgeuse, you can see it has a distinctly red tinge to it. And so that tells us the surface temperature of these objects. So immediately that colour tells you that surface temperature of the star. So most normal stars like the sun, when they're first born, they produce energy through fusing hydrogen to helium. And this can only happen in the very, very hot interiors where the temperatures are high, the pressure is high, and the densities are high. So in that hot core, in the very centre of the sun, we can get the fusion process occurring, where we have 4 hydrogen nuclei, which are protons. They come together at high temperatures, high pressures and high densities, and they fuse together to form a helium nucleus, which is 2 protons and 2 neutrons that are fused together by the strong nuclear force. So this is a nuclear process that occurs at high temperatures. So that's why we call it thermonuclear fusion. So these protons, if you weigh these protons, these 4 protons, and you compare it to a helium nucleus, you'll see that a helium nucleus weighs slightly less. So going from the 4 protons to the 1 helium nucleus you've actually lost some mass, and that mass gets converted to energy by Einstein's famous equation E equals mc squared. So by taking a little bit of mass and multiplying it by the speed of light squared, we get a large amount of energy out. And so a star like the Sun will be fusing hydrogen to helium in its core, releasing this energy from converting a little bit of mass to energy. And when we look up at the sky, most of the stars spend about 90% of their lives on the main sequence, and they're fusing hydrogen to helium while they're on the main sequence. It's only near the ends of their lives, which happens at various stages depending on their masses. So at the end of their life, other fusion processes can take place. So for something like the Sun will spend about 10 billion years on the main sequence doing this fusion process. So stars are born with a variety of masses. I've said this before, and their evolution depends on when they run out of fuel. So stars evolve because they run out of the fuel in their core. Now, for some stars like the Sun, that will take 10 billion years. But for a high mass star, their luminosity is so high that even though they may have 10 times the mass, 20 times the mass of the Sun, they run through that fuel very, very quickly, and they have very short lifetimes. Whereas if you consider a very low mass star, maybe a tenth the mass of the Sun, the luminosity is very, very low. And because they're fusing the hydrogen at a very low rate, have a very low luminosity, their lifetimes are hundreds of billions of years, so much longer than the current age of the universe. So massive stars are a bit like rock stars. They burn bright and die young, but actually saying that, there's lots of rock stars that don't do that these days. They seem to come back, and stars don't tend to do that. So the Sun will live for 10 billion years. It's now about halfway through its life. It's about 5 billion years old. So it still has another 5 billion years left in it. A star that has 25 times the mass of the Sun will only live for 10 million years. And in terms of astronomical timescales, that's very short. 10 million years, and then it's run out of fuel. It will need to evolve. Something happens to that star. A star, one of those little red ones, a star with a tenth the mass of the Sun will live for 1,000 billion years. And remember that the universe is about 13.7 billion years old. So once you form one of those little red stars, they hang around for a long time, many times the current age of the universe. Okay, so I want to talk about two basic paths in stellar evolution. So when we talk about stellar evolution, I said I would give two examples, and there's two pathways generally that you can talk about. So from a nebula, we can look at the low mass sequence, which is something like the Sun. So something like the Sun will be a yellow main sequence star, and it will have about 1 solar mass. And the other type of evolution I want to talk about is a high mass star, so maybe something that's 20 or 25 times the mass of the Sun, is much more dramatic, and we'll talk about that as a different pathway. So first of all, I want to look at this top pathway, and this is what evolution the Sun will undergo. So initially, it's born from a cloud of gas and dust, probably as part of a star cluster, and the Sun would have formed with a group of stars at the same time in a star cluster. So when it's on the main sequence, for 10 billion years, it will fuse hydrogen to helium in its core. And so it spends a long time, 10 billion years, doing that as a main sequence star. And that's really important for us here on the Earth. We need a star that's nice and stable, that gives us time for the planetary system to form and for life to evolve on the surface. So the sun will eventually run out of hydrogen fuel in its core, and when it gets near the end of its life, it will run out of hydrogen and it will turn into a red giant star. And this red giant star may be 100 to 300 times the size of the sun as it is now. And it will fuse helium to carbon in its core. The core gets hot enough for the helium, which was the product of the hydrogen reactions. That helium can actually ignite and form carbon in a separate fusion reaction in a red giant star. And that's all the fusion reactions that can take place in a star like the sun. After it's become a red giant, it becomes unstable, usually starts pulsating, and it starts throwing its outer layers off into space. And then you'll see the object that we call this a planetary nebula. At the centre, there's the hot core of the sun. It may have about half a solar mass of material there left over, and then you'll see the outer layers that have been puffed off the star. They will glow because that core of the star, of the sun that's left behind, will illuminate the gas clouds that have been thrown off, and that will mean that this will glow as this pretty object called a planetary nebula. And we can see here blue and red light emitting from these layers that have been thrown off the star. And then that hot core of the star will be left behind as a white dwarf star. So this is the hot, dense, dead core. Essentially, no fusion reactions are taking place here. It just cools down over time and becomes less luminous and becomes cooler. So that's essentially a low mass. A star like the sun will do that. So in about 4 billion years, the sun will turn into a red giant star. So if it starts off here as a small average garden variety star at 5,800 Kelvin as its surface temperature, then in about 4 billion years it will puff up into one of these big red giant stars, 100, 200 times, 300 times its current size. And the surface temperature, even though the core is much, much hotter than it used to be, the outside surface temperature is cooler, and so that's why it looks redder here. So it's about 4,500 degrees on the outside. And the fusion reaction that's occurring in the centre is the helium that we produced initially from the hydrogen fusing to helium. Now the centre of this red giant star is hot enough that we can fuse 3 of these helium nuclei together, and that will form a carbon nucleus. So we call this the triple alpha reaction because helium nuclei are often called alpha particles. So you have 3 alpha particles, they come together, high temperatures, fuse together to form a carbon nucleus. And that is also a fusion reaction that gives off energy. And so once again, the difference in mass is converted to energy. So that's the process that occurs. Now, also you can add a helium onto carbon, and you can form some oxygen at the same time, but mostly it's helium to carbon is the fusion reaction. Now that will, the red giant will only last for about 1 billion years, and then that's all the fusion reactions that can occur in the sun. The sun's core doesn't get hot enough for any more fusion reactions to take place. So that's the end of fusion for the sun. So at that stage, the sun will become unstable or throw its outer layers off into space, and depending on the orientation of the star, if it's in a binary system or how it's orientated in space, you might see planetary nebula looking something like this series of images. Some of them are spherically symmetric, and some of them have these sort of hourglass shapes. Some of them are bipolar. And as I said, some of that is due to binarity. If it's in a binary system, some of it might be due to magnetic fields. So the final remnant will be the star's core, and it's left behind in the centre of these planetary nebula, and there's usually a hot, dead, but very dense object left as the white dwarf star, the dead core at the centre of these objects. these white dwarfs are really weird. They have the mass of maybe half a mass, or up to maybe a solar mass of material, but they're only the size of the Earth. So they're incredibly dense. So if you have a whole solar mass of material but squeezed into something the size of the Earth, then they are very, very dense. Now remember, they're the dead cores of stars, so they're mostly made of carbon. We've fused the helium together to form carbon. So these are carbon under high pressure and high temperatures. So what happens to carbon when you put it under high temperatures and high pressures, and are very, very dense? And this is from a press release a few years ago. People were looking at these white dwarf stars and looking at the pulsations in them. And they found out the interior structure of a white dwarf star has a crystalline structure that's somewhat like diamonds. So the nursery rhyme, "Twinkle, twinkle, little star, how I wonder what you are, up above the world so high, like a diamond in the sky," is actually quite relevant for some stars. These white dwarf stars, which have this somewhat crystalline structure, forming as they form and cool down over time. So yeah, maybe space mining is worth it. I'm not sure. Yeah, get one of those as a solar mass of diamonds and bring it to Earth. Okay, so that's the evolution of a star, what we call a low mass star, like the Sun. Now we want to consider the life cycle of a high mass star, maybe 25 times the mass of the Sun. So once again, they form at the same time, usually as a cluster of stars. There's some big ones, some little ones. If you have a high mass, a big mass star, a high mass star, it will be a big blue star. Okay, high luminosity, high mass, and it will burn through its fuel very fast. So 10 million years, maybe a little bit more, and it uses up its hydrogen fuel very, very quickly. So it then fuses helium, turns into what we call a red supergiant, and fuses helium to carbon. But these stars are so massive that their temperatures at the centre are hot enough that other fusion reactions can take place too. So carbon can fuse to other things, heavier elements, that heavier and heavier. So you can have silicon, oxygen, silicon, neon, magnesium. Those type of elements can fuse in this hot core of this red supergiant star. And lots of these fusion reactions take place at these very, very high temperatures, all the way up to the elements up to iron 56 and nickel, around the same mass. So it's a red supergiant star. It's got an interesting structure to its core. The core is very hot, and all these fusion reactions up to iron have taken place. Now, once iron forms inside the star is doomed, because all those fusion reactions, hydrogen to helium, helium to carbon, carbon to heavier elements, and all the way up to iron, those are all reactions that give out energy. They're all exothermic, they all release energy, and so they are fuel sources for the star. But once you get to forming an iron core, there are no more fusion reactions that can take place that give off energy. All the reactions higher than iron actually require energy for the reaction to take place. And so in that case, any further fusion reactions will drain energy from the star. And so at this point, once our iron core forms inside this red supergiant star, the star is doomed. So within a day, that iron core will collapse. And that implosion of the core causes explosion of the star. And the star will explode as a supernova and will be seen very, very bright. You can see them in far distant galaxies because they're so luminous. And then there's two interesting end products of a supernova explosion. You can either have a neutron star, which is even weirder than a white dwarf. It's like a white dwarf, but that has been compressed even more until it's just neutrons. We'll talk about that in a wee while. And then if it's even higher mass than that, this neutron star can collapse under its own gravity to something called a black hole. And a black hole is black because essentially no light can escape from it. And so it's dark or black because we can't see anything coming from it. So when we look at one of these red supergiant stars and we look at the actual structure of it, the star is very extended, very low density, except the core is quite dense and quite interesting. So it has, on the outside of the core, it has non-burning hydrogen, and then it's got a layer of hydrogen fusion. So hydrogen is fusing to helium. Inside that we have helium fusing to carbon. Inside that we have carbon fusing to heavier elements, oxygen fusing, neon, magnesium, silicon. And inside the center, what's falling to the center is this end product that doesn't give off energy, this inert iron core. And as I said, once that iron core forms, that star is doomed. So this onion skin structure, as it's known, is the small, very dense core, and then you have this very extended low density envelope around it for these red supergiants. So any star that's about 8 times the mass of the sun or more will go through this high mass cycle of stellar evolution. So we've formed an iron core. That iron core collapses. It becomes very dense. It infalls, and we get this compressed core forming. Things called neutrinos are released at a certain stage, and then the outer layers fall into the star, and then there is a implosion and an explosion. So this compressed core is often left behind as a neutron star, and one famous supernova explosion that went off in 1987 that some people may remember. So this is the LMC. This is a supernova explosion. This is a nearby galaxy, the Large Magellanic Cloud, that is a small galaxy that orbits our galaxy. And this was the brightest supernova for about 400 years because it was in a very nearby galaxy. So this got to magnitude about 3. It's quite obvious to the naked eye. And when Hubble Space Telescope imaged it, you could see the two, essentially an hourglass figure. This is sort of 2 lobes of material that have been ejected and from this stellar explosion. And people have studied the way in which this explosion has evolved over time and taken numerous photographs and movies, essentially put together lots of images to see the evolution of this supernova remnant, as we call it. Okay, here's another supernova remnant. This is a very nice image. You can see it really does look like an explosion. So this was recorded in 1054, the year 1054. It was recorded by Chinese astronomers who said that there was a guest star in the heavens, and they listed where this was observed. And then in recent times, astronomers pointed their telescopes to the region in the sky and were able to see that indeed this was a supernova explosion, and there's this remnant of exploded star there. And at the center of the Crab Nebula, there is the neutron star that we have left over from the stellar explosion. So low mass stars end up as white dwarfs, which cool down over time. They're the dead cores of stars. And high mass stars end up as neutron stars or as black holes. And I'll just explain those in a little bit more detail. So a neutron star is a star made of neutrons. So the iron core has collapsed down. And so essentially what you're doing is you're taking electrons and protons, which usually you have electrons orbiting around your protons, an electron cloud. So in a neutron star, these two things are squished together to form neutrons and neutrinos, and then the neutrinos are packed. The neutrons are packed very close together, and this quantum mechanical pressure, neutron degeneracy pressure, holds up the star. So to compare with a white dwarf, if you have the Earth and you have a solar mass white dwarf, it will be about the size of the Earth, maybe just a little bit smaller. But if you have a neutron star, essentially you're squeezing all the air out of your atoms and you're turning them into neutrons, and then you're packing those neutrons really close together. So you form this solar massive material at very high densities, the densities of the nucleus of an atom, and these are incredibly dense objects. So a solar mass of neutron star material will only be 10 or 20 kilometres across in size. And it's interesting to make a comparison of densities. If you think about a cubic centimetre, centimetre by a centimetre by a centimetre of water, if you weigh that, that weighs about a gram. And if you take a centimetre by a centimetre by a centimetre of material that's the average density of the sun, that will weigh 1.4 grams. Okay, so a little bit heavier than water, but not much. If you have a centimetre by centimetre by a centimetre, cubic centimetre of diamond, then that will weigh 3.5 grams. So 3.5 times more than water. And if you have a cubic centimetre of white dwarf material, that will weigh 2.3 tons. And if you have a cubic centimetre of neutron star material, it will weigh 230 million tons. So that's really dense. It's an incredible amount when you compare it with something that we're more familiar with. So these are really completely strange, weird, super dense objects. How do we actually detect neutron stars? It's quite difficult. They're not that obvious to see, and we tend to see them in two different ways. Either in a binary system where we can look at a neutron star orbiting something else, and from Kepler's laws we can work out what the masses of the two objects are, and we can often see a neutron star pulling material off a companion star, like in this diagram, and this material gets accreted onto the neutron star, or in this case you can see here it's a white dwarf pulling material. The neutron star is pulling material off the white dwarf and it's accreting it, and that, as I said, the orbit of this binary system allows us to work out the masses of those two components. And the other way we can see neutron stars is if they're rotating. Now, a neutron star, they tend to be, because they've collapsed, they tend to spin up as they collapse because of the conservation of angular momentum, and that concentrates the magnetic fields. So often neutron stars are highly magnetic and they're spinning very fast. And if the axis of rotation and the axis of the magnetic field is offset, then we can see the magnetic fields constrain the radiation along certain lines, and this, as the neutron star rotates, we can see this star give off radio pulses or pulses of light even. We tend to pick them up in the radio, so they give off radio pulses. And the model for this is called the lighthouse model. So if we have here a neutron star rotating round, it's giving off energy constrained along the magnetic field lines, then as it flicks past our point of view, we can see the light and we can also see the radio waves. And this is called a pulsar, a radio pulsar or a pulsar. And that's an easy way to detect these rotating neutron stars. If the remnant is more than about 3 solar masses, then the neutron degeneracy pressure can't keep the star up as a neutron star. So gravity wins, and the neutron star collapses to something called a black hole. And that black hole is black because the escape velocity is greater than the speed of light, so not even light can escape from a black hole. And once again, the way to detect these is in a binary system. So if you have a black hole and it has a star orbiting it, sometimes it pulls material off its companion star. This forms an accretion disk around the black hole, and we can work out what the masses of these two components are. And often this black hole may be 5 or 10 solar masses. We can't see it. So it has to be something weird like a black hole. Okay, so a white dwarf is about the size of the Earth if it has about a solar mass of material. A neutron star is about 10 or 20 kilometres across, maybe the size of a city. And a black hole has no size at all. It's collapsed down, gravity's 1, and no light can escape from a black hole. So just to finish up, I wanted to talk about tying back stellar evolution to how we understand our place in the universe. So in the beginning, there was the Big Bang. We have a universe that expands with time. So this was a discovery from the 1920s when Hubble found that the universe wasn't unchanging and infinite. It actually was expanding. So because the universe is expanding, if you go back in time, the universe would be smaller and hotter and denser, and there has to have been a Big Bang at some time in the past, 13.7 billion years ago. And since then, the universe has been getting bigger, expanding and cooling with time. Galaxies have formed and stars have formed in those galaxies. So we can think of galaxies as big cosmic recycling plants. They form generations of stars in the spiral arms, and these stars form as clusters of stars. They evolve depending on their mass, and when they die, either as a supernova, which spurts off lots of very processed material into space, or even if they die as a planetary nebula, they throw off at least half their mass into space of processed material. And so these life cycles of stars create the heavier elements. So in the Big Bang, there was just hydrogen and helium, whereas as stars go through their evolution, they're forming the heavy elements. So everything that's not hydrogen or helium, the carbon and the oxygen and the silicon, that's all formed from this process of stellar evolution. These fusion processes occurring in the hot cores of stars. So many generations of stars have to have lived and died in the Milky Way to build up this abundance of heavy metals. And it's quite interesting that we can these days understand where the different solar system elements the different elements we see in the solar system, where we understand where these can come from. So the Big Bang produces hydrogen and helium, and these other heavier elements come from different types of stellar evolution processes, either massive stars that explode or white dwarf stars that explode, or even dying low mass stars like the sun. And just recently, we've seen the merging of neutron stars and seen their signatures from gravitational waves. We understand that they're important for forming some of these heavier elements like silver and gold and heavier elements. So the Big Bang made hydrogen and helium. The stars and the life cycle of stars makes everything else. And so in order to form a solar system, we need heavy elements. We need the silicon, the silicates to make the rocks. We need the iron and nickel to make the iron core of our planet. And so for our planet to have formed, there has to be a certain quantity of heavy metals in the gas cloud that formed our solar system 5 billion years ago. And that's the only way you can get these rocky planets forming. And then if the rocky planet's existing at the right place in the solar system, then liquid water can exist on the surface of the planet. We can have the water cycle, and we can have life evolving on the surface of the planet, and we can have astronomers who can observe the universe and see these processes happening in other distant stars and star systems. So there we have our Earth sitting in what we call the habitable zone, just the right place where liquid water can exist around our sun. The habitable zone will be different places depending on what star you're orbiting around. So it will need to be further out for a hotter star and further in for a cooler star. Okay, and the possibility of life's intriguing. We've started to find many, many thousands of stars, and so many, many thousands of planets around extrasolar planets around stars in our galaxy. And so the numbers are looking very good for thinking about how many of those are in habitable zones, and therefore what the possibility or probability of life existing can be. Okay, and then space travel's hard, but one day we may be able to find, maybe not by going there, but at least by detecting the signatures of life on extrasolar planets. So I just want to finish up by giving a quote from Carl Sagan, who is one of the people that inspired me when he made his Cosmos series and talked about astronomy. We are made of star stuff. For the most part, atoms heavier than hydrogen were created in the interiors of stars and then expelled into space to be incorporated into later generations, into later stars. The sun is probably a third generation star. So I just wanted to finish up by saying that in a very real sense, we have a very strong connection with the stars. So when people talk about humans being the children of the stars, that's true in a very real sense. We can see that we have a special connection with them, and we wouldn't be able to exist in terms of the carbon in our bodies, the oxygen in our blood, the calcium in our bones. All that has to have come from various generations of stars, which were around before our solar system was created. So we're all made of stars. We're all star stuff, and that's where I'll finish my talk and say that's the end of that star. And I believe that there are questions that can be asked if you would like me to talk about anything more, and to ask those in the chat box for this talk. Just use the chat box, and I think those questions will be asked if you would like.
Thank you very much, Karen. That was a fantastic presentation. I certainly enjoyed it, and I'm sure our viewers did too. I've got a comment and a question so far. There is time for some more questions if people get in quickly on this one. Firstly, the comment, and not sure if you have, you mentioned the stellar disk of Beta Victorious is one of your favorites. I'm not sure if you're aware that one of our society members, Rolf Olsen, was the first amateur to actually image the disk.
Wow.
So he's actually doing a talk next month in your slot next month.
Oh, I have to watch that. It sounds fascinating. Yeah.
So yeah, do check out Rolf Olsen if you've not seen his photo. The first amateur to actually image that directly.
Oh, it sounds great.
We also have a question, and it's a question regarding pulsars, and our viewer wants to know what causes their rotation rate to slow down as they age. So, i.e., by what mechanism do they lose their angular momentum?
Okay, so as the star collapses, they speed up because of angular momentum conservation. And if they weren't losing energy, they would just keep rotating at the same rate. But they are losing energy. Essentially, they're giving off energy because we see the radio pulses, we see the electromagnetic radiation that they are releasing, and they're also quite magnetic. So they're losing this energy as they're aging. And so because they're losing energy, they have to slow down in order to conserve conserve angular momentum, and that loss of energy goes into what we see in terms of the radio pulses, but it also causes the whole system to slow down.
Fantastic, thanks for that. There aren't any more questions on the chat at the minute. If there's any more, just come through very quickly. Doesn't look like it. Thank you very much again, Karen. I really enjoyed your presentation, and hopefully you can make it up to meeting in Auckland at some point. Oh, we have actually just got 2 more questions that have just jumped in. Often happens.
Yep.
So a question from John Drummond. He asks, during solar nuclear fusion, when 4 hydrogen protons merge under pressure, what causes 2 of them to become neutrons while 2 remain protons?
Oh, okay. Yeah, that I kind of simplified that. So that process of 4 hydrogens coming together to form a helium nucleus, that's actually a 3-step process. So first of all, you have hydrogen. The first step is a hydrogen. You add on another, bangs into another hydrogen, and it forms deuterium. So it forms one of the protons gets converted into a neutron, and you form a proton and a neutron in the nucleus, and so that's deuterium. So that's like heavy hydrogen. And in that process, a positron is emitted, so an antimatter particle, and that's because you have to conserve charge. So that's the first step of the process, and then you have a deuterium. Another proton bangs into that, and that forms helium-3. So helium-3 is 2 protons and 2 neutrons. So in that process, once again, you've got the 2 protons and the neutron. They've formed this 3 helium nucleus. That's the second step. And the third step is 2, 3 heliums come together, and one of the that forms a 4 helium nucleus, so 2 protons and 2 neutrons in the nucleus, and then that spits out 2 hydrogens, two protons, and they spat out, and they can take part in the next series of reactions. So it's actually a 3-step process. You don't actually have 4 protons come together in one big go. It actually takes several different steps, and the first step is very slow. That's the one that governs the rate that reaction is going to take place. So in each of those processes, you add a proton to build up to eventually to the helium nucleus. Did that answer your question, John?
Hopefully it does. He might comment on that. And we just got one more question from Jason, who wants to know, do pulsars emit approximately the same frequencies? If not, why not? And if not, does that imply anything about the pulsar's origin?
Okay, so generally the easiest way to see a pulsar is in radio waves. So they were first discovered because they were they were clock-like pulses that were seen from a cosmic source. And initially, when people discovered them in the 1960s, it was the beginning of radio astronomy, and they found these very regular radio pulses, and they called them LGM, little green men, because they thought they were alien civilizations signaling the Earth. But in actual fact, they're just very efficient clocks. Because they're a rotating neutron star, they're giving out radio pulses, and the young ones are rotating quite fast, and they slow down over time. And then if they're in a binary system, they can spin up even faster. So they give off they give off radio waves, but some of them also give off light waves. So they give off different frequencies of electromagnetic radiation. But they're generally strongest. We generally see them in the radio. And the timing, so the periods of them slows down over time, so that we can do an age based on the pulsar spin down time.
Fantastic. And with no further questions, I just want to thank you once again, Karen. Great
Okay,
presentation,
good.
and hopefully we'll see you up in Auckland for a live presentation sometime.
Yeah, that would be good. Look
Thanks.
forward to it.
Thanks very much.
Okay, thanks.